Thank you very much, Matt, and thank you very much to the organizers for putting together this wonderful event. So I'm going to talk about CD indices and semi-Eulerian posets, and I'm going to try to use the board. So bear with the crazy yoga that's going to happen here, trying to move things. So everything I'm going to say is joint work with Martina Juhnke, who is around here, and Lorenzo Venturello. And so, quick question. Does anybody know what the CD index is?
Once.
And is anybody scared of the CD index? Okay, so, so Martina told me to tell you not to be so scared. That was a nice trick that I'm going to copy from her. But I'm going to try to tell you a story. It's very technical, so I'd much rather tell a story of how this goes and what are the objects behind and what's kind of the point of the things that are going on. And tell you, like how to navigate the world of the CD index. That's my goal, and I hope that you become a little less scared of thinking about it. So where does this story begin? I'm going to talk about, so I'm going to talk about posets. So P is going to be a poset. I'm always going to assume that it is graded. Bounded. It means I have a 0, which is a minimum, and a maximum, which I'm going to call 1. I'm going to assume that it's graded, meaning that every saturated chain from 0 to 1, from the top to the bottom, has the same length. And I'm going to assume that it has rank n plus 1. That is, the number of elements in this chain is always n plus 1. No, n plus 2, because I want this to be, so I want 0 to be rank 0. And let me start telling you what are the objects that I'm going to be talking about. We're going to say that P is Eulerian first. If for all x less than or equal than y, there's two different ways of saying it. I could compute the Mobius function of the poset and say, well, this is going to be the rank of x minus the rank of y. If you don't know what the Mobius function is, what you should think about is I could look at the interval in the poset, everything that is sitting between x and y, and I could count how many elements are there of even rank. I could count how many elements are there of odd rank, and I want those two numbers to be the same. Okay? Even rank elements equal to number of odd rank elements. And then, so that's an Eulerian poset, and I'll tell you a little bit how to navigate the Eulerian posets in a second, but I want to talk about semi-Eulerian posets, and the difference is not that dramatic. So semi-Eulerian, it is exactly the same, except that I'm not going to ask that this is satisfied for 0 and 1. Drop condition for 0, 1. Okay? So what should you have in mind when I tell you this? The idea is, well, this condition, so Eulerian, one should think of as this is a poset where I'm prescribing a lot of local information. So if you think about, I can, let me define something. This thing over here, this is the order simplicial complex of P. And so what is this? So vertices are elements of P minus 0, 1. And faces are chains. Okay?
So you keep leaving out 0, 1. Are you ever going to actually use them, or are you just dressing up for near prime?
Yes. So in particular, I want to compute the Mobius function to, in 0, 1 to tell you how this differs. And so, so I'm going to look at this order complex. And so being Eulerian is a condition. So Eulerian in a big picture, it's a condition about a ton of local information. And by local, I mean look at links. Links of faces, plus a global information. So plus some global restriction. I want to think of 0, 1 as some global restriction. I'm going to tell you the story in a second. You could think of this as the link of the empty set, if you know what that is. But in a sense, so what all these counts are telling me is there's some local information, and in the Eulerian case, there's also a global thing.
Yeah, just to clarify, so you're saying that your semi drops the
global.
That one long chain from 0 to 1, but you're still looking at like 0 to elements inside the set. That's allowed.
Yes.
Okay.
So everything is allowed except the top, the big thing. And so the way how I want to think about it is Eulerian is local information, semi-Eulerian, local information and one global condition. And semi-Eulerian is I'm keeping only the local information. Okay? So that's the things that I want, or those are the things that I want to talk about. And now let me tell you a little bit of how to navigate these. So the way how I want to think about this is there's many realms in which I can think about posets. I can think about them in terms of geometry, topology, algebra, and combinatorics. And I think this contains all the words in the title of the conference. Oh, and computation. Yeah, but what I'm going to do is difficult to compute. So I hope it counts. But the point is, so we could think about geometry, and if I want to give you an example of an Eulerian poset, our favorite should be take the face poset of a polytope. And that's going to be Eulerian. What this is telling us is that the Euler characteristics of the faces behave the way one should expect them to behave. And if we think about geometry, I could also think, well, maybe I could think about topology. You know, like the magical thing that works here for polytopes is that they're somehow spheres, and I could think, well, maybe I can think about, let's say, triangulated spheres or CW spheres if you want. CW, if you know what that means, it's okay. If not, think of regular CW spheres or glue together a bunch of polyhedra to form a topological sphere and ask that the boundary is something homeomorphic to a sphere. And if you want to think about algebra, and it's kind of sketchy what or it doesn't sound too much like algebra right now, but I can think of homology spheres. And so here I'm thinking really geometry, convexity. Here I'm thinking I want a space that topologically is like a sphere. And here I want to talk about homology spheres. And what's a homology sphere? If I look at homology globally and locally, meaning I look at homology on the links, how does the complex behave around the face, and how does the complex behave in general, it's indistinguishable from a sphere. If I look with homology, I do not distinguish those things. And then there's Eulerian, and what Eulerian is, I want to call it combinatorics, it's this counting condition, and essentially what it's telling me is I can look to the complex with the lens of Euler characteristics, and the Euler characteristic is dumb enough not to tell that this is not a sphere. Okay? What I want to do, and so the way how one thinks of semi-Eulerian complexes is I want to add a different column here because it feels like there's topology, and so here in geometry I don't know exactly what I want, but maybe some nicely embedded manifold. Because here the magic of polytopes is that we are able to use geometry, we are able to use convex geometry. So let's say that, or let's pretend I don't know exactly what it is, but maybe there's nicely embedded manifolds. But at the level of topology, I can think of, if you want, triangulated manifolds or regular CW decompositions of manifolds. And then I can think of homology manifolds, and this is exactly, it follows the same philosophy as a homology sphere. It's a space such that homology cannot tell it apart from being a manifold. It kind of depends, so this depends on a field. And semi-Eulerian is, well, the Euler characteristic cannot tell the difference between this and a manifold. And so to answer Dave's question, I really want to use the 0, 1 here, because the 0, 1 here, when I compute its Mobius function, is going to tell me I have a semi-Eulerian complex. It's kind of like a manifold. And I can, so the 0, 1 tell me what's the Euler characteristic of that manifold.
I have a new question. So in topology, people don't just study spheres, right? Is there an equivalence relation among posets? So the Eulerians correspond to spheres, but the other equivalence classes we can think of as...
It's complicated. So combinatorics is dumb, and so it's dumb enough. Let me tell you one thing that happens, right? Like I'm telling you that this is the Euler characteristic, and now let's think of an odd-dimensional sphere. Sorry, an odd-dimensional sphere, no, an odd-dimensional manifold that is not a sphere, and by Poincare duality, it has symmetric Betti numbers. You compute the Euler characteristic, you get 0, and so by accident, you get odd-dimensional manifolds here.
So they're not just spheres.
They're not just spheres. So there's way more stuff. So this captures a ton of different things. But think of any odd-dimensional manifold. Poincare duality tells you it accidentally falls here, right? But I really want it here or here. Okay. So the idea is, well, we can study the combinatorics, the topology, the algebra of these things, and say, or study properties of P through the lens of different fields of math. The reason why I'm calling this algebra is I'm computing homology, but in the secret, in the background here, this, so the correct word for this is, it's usually called a Gorenstein star poset. And what this is telling us is, look at this simplicial complex. And so it's going to have something to do with Eulerian, but I also wanted to ask, I also wanted to be, so this is in general Eulerian plus Cohen-Macaulay, and here I mean the Stanley, and I know that people have been debating whether it's Reisner or Riesner, but there's a lot of people who speak Spanish here, so let me add entropy to the mix and call it Reisner.
Go for it.
So Stanley Reisner rings. And so, when one studies this, the nice thing about studying this is, well, recognizing spheres is very difficult, but I can try to recognize homology spheres, and computing homology is easier, and on top of that, I get a ton of tools from commutative algebra to deal with this. Here, we also have a nice class of rings that corresponds to this. It's called Buchsbaum rings. I can think of the order complex of these, I can ask for homological conditions, and I can do a little bit of commutative algebra to study those things over there. So what do I want to study?
You're walking away without doing that corner.
Huh?
Well, Stanley Reisner, is that what you said? Is a famous ring associated to a simplicial complex.
Yes.
What's the famous ring associated to the Eulerian poset? There should be something.
There is, it's complicated. But you essentially do a sheaf on a poset, similar to what Jonathan was talking. Or, I mean, there's a ring, it's complicated, it's hard to present, yeah.
So put a squiggle in that corner.
Yes. Yes, but in general, semi-Eulerian, I mean, the Euler characteristic doesn't know enough, you're forgetting too much. And Buchsbaum, yeah. So what do we want to study? Let me talk about flag enumeration. And I promise an example is coming soon, but it's gonna, so bear with me for a second. So I'm gonna think about, I'm going to talk about a vector, and this vector has one entry for every subset of n. Remember that my poset had rank n plus 1, so every relevant element that is not 0 or 1 has one associated rank, which is a number between 1 and n. And so what I'm going to do is I'm going to think of SF of P for an Eulerian or semi-Eulerian or for a graded poset in general. This is going to be the number of chains in my poset. X, let's say X cardinality of S, such that if I look at the rank of my elements, I get exactly the set S. Okay, so I'm going to count chains. If I want to count what's F, I don't know, 1, 3 of P, what I do is I count how many elements are there, how many chains are there with one element of rank 1, one element of rank 3. So it's like an F vector. It's a refinement of the F vector of this simplicial complex over here. And we know that when we study F vectors, there's something nicer. People in commutative algebra like it, know it very well, much better than me. But there's a companion vector here, which is the H vector of this thing over here. And the way how one defines this is as follows. I'm going to define HS HS of P to be the sum over the T subset of S of minus 1 to the S minus T F of T of P. And if you want, this looks, I mean, it's not very confusing. It's an alternating sum on cardinalities, but we can also think about this as, so it's invertible, it's the same information, and the way how we compute F is much easier. What we do is we add things. Okay, so the H's are numbers that add to the F's when you sum over all the subsets.
Maybe you want to swap S and T in the indices.
Yes, correct. T subset of S. You're right. Thank you. So let me show a small example. I had planned a bunch of things, and then I realized that I cannot use this part of the board, so I had to modify my plan a little bit. But here's an example. I took a polytope. This polytope has a phase poset, and I already pre-filled a few of these layers. So I can try to think about what's the flag F vector of this polytope, and I can try to count things, right? So for example, here I have the set 1. This corresponds to elements of rank 1, which are vertices. I have 5 vertices in this pyramid over the square. F2 tells me how many edges, and I pre-computed, for example, F13. What I want to do is I want to count how many incidences do I have between a facet and a vertex. So I have, for each triangle, I have 3 incidences. I have 4 triangles, that gives me 12, and I have the bottom square, that gives me 4 extra, and I get a 16. And if I know this information, it's pretty easy to compute H. What I need to do is I want to make sure that the sums that are not visible, but the sums work well. So for example, if I want to compute H here, I want to make sure that H empty plus H1 equals 5. So in this row, I get 1 less. And if I wanted to compute H13, I would have to make sure that these one plus these one, so 1 plus 5 plus 5, no, sorry, 1 plus 4 plus 4 plus 7 is equal to 17. So this is 9 plus 7. There's a unique way to fill this table, right? And so we would like to understand them. I would like to understand these vectors, say something, and if you observe this for a little while, you'll realize maybe that there's a lot of symmetries, and there's many nice properties, you know, like if we have a sphere, we have dense real equations, and here we have some sort of symmetry. If you look at, for example, there's 2 7s over here, there's one that corresponds to a 2, and there's one that corresponds to a 1 3. And it turns out that the union of these two is the entire set. So there's a symmetry and there's more stuff. So what I want to do is I want to keep track of this thing in terms of, or define a good way to keep track of this information.
Can I ask a quick question? Is there, maybe you're like too far away from it at this point, but is there a way for me to think of what the poset is? Or like how to think of this as a poset?
The phase poset. So I have the empty set, which is, so the zero is like the empty set. My atoms are vertices. My edges are elements. So for example, this edge would be above this vertex because it contains it, but it would not be above this one because it doesn't.
What's the drawing on the right?
Huh?
What's the drawing on the right?
Ah, wait a second. It's,
Okay.
Don't look at it. So what I want to do now is I want to keep track of this, and the way how one does this is with a little bit of non-commutative rings. So I pre-wrote this not to spend too much time, but I can think of polynomial rings in two non-commutative variables. So A, B are going to be non-commutative variables. And if I look at these variables in degree n, well, as a modular, as a vector space over Q, this has rank n. And it has a monomial basis, which I'm going to denote by US for each subset of n. And the way how US works, this is slightly annoying notation, but maybe I can put some S's here. I'm going to say that US corresponds to the variable where I put an A if so UI, the ith monomial in this product is A if I is not in S, and it's B if it is, right? And so what we're going to do is I'm going to define to you an interesting polynomial, and I'm only going to do it for h's because it's more convenient, which I'm going to call psi of p, and this is the sum over the S subsets of n of, I'm going to use this monomial to keep track of my h's, right? And we know, or I mean, we see from this table here that there's some sort of symmetry, and maybe these polynomials can help me keep track of that symmetry. And so there's a trick. There's a trick that is quite interesting from. So it's a trick of Fine, and then Bayer and Clapper, which tells the following. I'm going to, for the sake of time, do this a little bit quickly, but I want to look at a variable of degree 1 and a variable of degree 2, and I'm going to build a graded algebra map that sends C to A plus B and D to AB plus BA. If you think about this, any element in the image is going to satisfy that silly or that symmetry that we saw in a few minutes ago. And so there's a theorem so this is fine, and there's no paper, but there's a very nice paper of Bayer and Clapper.
Different buyer.
Huh?
It's a different buyer, isn't it?
March Bayer. Yeah.
So,
I mean, unless you prove it and you don't remember which.
Oscar, you can't sleep here. Last time I saw Oscar was risky.
But what it says is that if P is Eulerian, so if P is Eulerian, there is, and in this case, so it's unique because that homomorphism there is unique. Phi P in C in two non-commutative variables such that this thing over here is equal to phi of this guy over here. Okay? So we can go back to the example. And what I did is I computed C cubed, CD, and DC in terms of ABs. And if you think about it for a little while, what you're doing is you're expanding a bunch of monomials, and every monomial is going to appear at most once, right? We have this AB, this BA. So if you open C cubed, that it would be A plus B cubed, then what you're going to see is that every monomial shows up exactly once. And then CD, so in CD, the monomials, for example, the monomial A cubed and AB squared will not show up. But the other ones show, so you expand it, you get 4 monomials corresponding to different sets. And nice exercise, you expand DC and you get the same, and those are all the monomials of degree 3. And if you think about it, there's a Fibonacci in the back. And what I'm saying, or what the theorem says, is that you can express this vector over here as a linear combination of these 3. This plus this plus this. And I wrote it here. The polynomial tells me, well, there's a C3 that goes over here. And here in HP, I had a 4. And there's, so for DC, there's a 1 here, and there's nothing else. I already subtracted a 1. So the DC is going to give me a 3 in this column. And if I look at CD, here I have a 0, here I have a 1. I already subtracted a 1. I get a 3 DC.
Sorry, I couldn't see any of that calculation. I could only see you.
Oh, sorry.
Good left-handed.
Yeah. So let's say I want to figure out what's the so C cubed has to be a 1 because there's only one element there. And so here, for example, if I want to look at DC, there's a 0, 1. So there's a 0 here and a 1 here. And so if I want to add up to 3, the only thing I can do is put a 3 in front of CD, in front of DC. So I get a 3 DC, and the same for the other one. And so the theorem essentially says that if you expand these things, they're going to get a lot of zeros, and you can fill, and if you fill the obvious choice here, it actually decomposes the entire thing. It's amazing. It tells you that there's Fibonacci many independent flag H vectors of Eulerian posets. And we could try to do the same for semi-Eulerian, and that's the picture over here. I drew a torus. I told you that the theory is supposed to work for manifolds. And so that over here is this thing here is a torus. I can play the exact same game. Now I have to remember that, for example, this vertex is the same as this vertex. But if I compute, I get 13 vertices, 22 edges, 9 two-dimensional faces. Now there's an octagon over there. And then there's 44, 44, 44, 88. And I try to play the same game. I get 1, 12, 21, 8. That's just subtracting 1. But now, for example, if I want to get 1, 2, I have to add 1 plus 12 plus 21 plus something equal to 44, and I get a 10. And here I get a 23, 14 minus 1. And this might be a little bit concerning. But if you look at it, and you stare at it long enough, you will realize that the symmetry here almost matches something here. Notice that 3, before it corresponded to 2, 3, and the difference between these two is 2. If I look at 21, so this corresponded to 2, and the complement is 1, 3, and I have a 23, and the difference is 2. If you look at 2, 3, there's a 12, and here's a 14, the difference is 2. And if I have an HQ, here I have a 1, and here I have a minus 1, the difference is again 2. Okay. So semi-Eulerian complexes or semi-Eulerian posets are not going to satisfy this theorem. But the point is, I can modify this a little bit and get it. How are we going to modify it? Let me. So the modification is, so here I'm going to add, so if I add a 2, I'm going to get an 11 here. And if you do the computations, I'm going to modify one entry of my entire thing. And so there's some balance, and so every set or its complement contains these 3. So if I change this by a little bit, it will change all the pairs that will give me the symmetry. And if I do that, this magically becomes, so this here will become a 10, and that matches the 10. This will become a 21. This will become a 14, and this will become a 1. It's kind of like magic. It's some linear algebra trick. I made a very strange choice of doing this at 3. And so we define that in general. So let me go here. I'm going to define so for semi-Eulerian, I'm going to define a modified statistic and say the modified f vector is, I'm going to do nothing if S is different from the largest singleton. And I'm going to do Fs minus the Euler characteristic of the, I think it's n minus 1 dimensional sphere minus mu p of 0, 1. So I'm going to correct by how much am I failing to be a sphere. If you think of the torus, the Euler characteristic of the sphere and the torus differ by 2. And that's the correction that I was making. So secretly, I can make that correction over there. And so let's call this F twiddle here. And if I do that F twiddle, then I have an H twiddle. And we can have a theorem. So this you can trace back to Ed Schwartz. And so we have some nice proof in the paper with Martina and Lorenzo, that now if P is semi-Eulerian, instead of, for a semi-Eulerian poset, what I'm going to do is I'm going to do this tweak. So manifold, I change a little bit with my Euler characteristic, and I can still find one of these guys. Okay? And it only depends on the Euler characteristic, nothing more. So what's the example here? Here's a 1, 12, 21, and here we had a 10. And if we want to do the same computation, well, I had a C cubed, because the only way to get the 1 over here is by adding C cubed, that's it. And now I have an 8 CD, and so CD is this one over here, and the way how you get that one is, well, I'm going to look at what's the entry here. It was an 11, but I subtracted that 1 coming from the C cubed, so it becomes a 10. What? Oh, I computed it wrong. So this one, no. Here I need a 10. Oh, it was right. And I subtracted 1 already, it becomes a 9. And this one over here was I needed to add to 12. I already subtracted a 1, so the DC becomes an 11. Okay? And so one can wonder, well, what's going on? And so let me tell you a few theorems about this. And so this is the time when I start improvising my board use, because I had to make a few changes, but. But let me mention you the prototype theorem that we like. So if you observe the computations that we did there, small, but if you look at the CD indexes, you get a bunch of positive numbers. And you get positive numbers that are much, much, much smaller than these other monsters that we wanted to understand at the beginning. So there's a nice theorem. It's due to Carew in 06 in full generality, but there's very nice proofs by Stanley. And I think this was 94 for polytopes or for triangulations, and that's going to be important. And it says that if P is Gorenstein star, then phi P of CD is coefficient-wise greater than or equal to 0. So I do this process, I get much, much, much smaller numbers. I know, so for let's say dimensional reasons, we know that we cannot get much smaller, or we cannot get less coefficients to pack all that information, and we get something non-negative, okay? So remember, what's Gorenstein star? That the simplicial complex in the back was Cohen-Macaulay, and actually the proof uses commutative algebra. And I told you that I made a random choice over here, and so if we want to make a random choice, we should justify that the choice that we made to make the change enforce the symmetry, that it is Eulerian, so it looks like a sphere, and the order complex is Cohen-Macaulay. So, or in other words, homology cannot detect that it is not a sphere. That's what you should think about. And the point is that there's going to be some algebra. This thing is false for Eulerian. So if you go to the broader generality of not having algebraic tools, it's not that you cannot prove it, it's false directly. But there's another very nice theorem by Stanley in 94. And what it says is, well, if P, so let's assume that P is Gorenstein star simplicial. And if you don't know what that is, you can just think of Cohen-Macaulay Eulerian complex and look at the phase poset. So if all my lower intervals, or if in the picture that I draw here of the space, I only see simplices, and or let's say this is the phase poset of simplicial complex, then, I mean, all the lower intervals look the same, so this contains way less information of a simplicial complex. Let's say, let's call it gamma because I already have a delta. What he does is, well, F vector theory falls inside this thing, and if I want to compute this guy over here, well, I'm going to be able to express this in terms of the original H vector, or the Hilbert series of the simplicial complex. So from 0 to n, Hi, and here you get some weird polynomials that I'm going to briefly address. But it's not terribly dramatic what this is, or it's not, the point that I want to make is defining this is complicated, but you can retrieve, in the case that you have something that is simplicial, this actually computes so you can compute this CD index from the H polynomial, from the thing that comes from the original simplicial complex. And the point is that Stanley showed that these polynomials here, so these are non-negative. And so before the proof of Carew, which is complicated for various reasons, the first partial result that came into into proving this thing, which had been conjectured before by Bayer and Clapper, was that for Eulerian complexes that are Cohen-Macaulay, this thing is non-negative.
So these polynomials depend on what?
So these polynomials, I'm not going to write it, but you take the simplex, and the n-dimensional simplex, and it has exactly n pure subcomplexes. Take one on its boundary. So you could take one facet, you could take two facets, you could take three facets, and those are all balls. And so if they're a ball, they have a boundary which is a sphere, and I attach one thing. So it's like I construct the boundary of the simplex one step at a time, and I figure out how much the CD index changes. It's a computation. It's a little bit ugly, but it's messy, but it works. And so the point, or the reason why we choose this change over here is the following. So if P is semi-Eulerian, or and simplicial, and you should think of, if I have a triangulated manifold, then the CD index that we defined with this funny modification still satisfies this. Exactly the same equation. Okay, so you figure out how you build the simplex, you have an H vector, and you write it like that. So we would say maybe, bingo, we win, and we can say something for semi-Eulerian posets and positivity, but that's false. Okay?
Jose?
Huh?
So if you're semi-Eulerian simplicial, like, you're talking about the face poset of a polytope, right? In some sense, like, if I want to think about this example, I guess I'm just wondering.
So I'm saying Eulerian.
No, semi-Eulerian.
Semi-Eulerian, I'm thinking of a manifold. I'm thinking of the torus, for example.
Okay. I guess I'm thinking simplicial polytope.
Simplicial polytope would be this over here. So this is simplicial polytope, and this is triangulated manifold. Right? So you would think that this is. So it seems like it would be. So the problem is that this might be. This may be negative. You don't have Cohen-Macaulay, you have Buchsbaum. Or no. In general, no. You can do this for any semi-Eulerian, but I can ask for a manifold, and the analog of Cohen-Macaulay for manifolds is I say that my Stanley Reisner ring is Buchsbaum. So in general, even if we have a nice manifold or some place where we can actually do the commutative algebra, this does not imply positivity. However, theorem, if P and is a phase poset of, now I'm going to say simplicial, and don't worry about this word, I want to say manifold. I'm going to change from polytopes to manifolds. Then this guy over here is again greater than or equal to 0. It's kind of crazy. I mean, think here in this H vector we got a -1, and for the general F vector of the triangulation, we can get a bunch of negative numbers, and we don't have much of a grasp of what this thing over here is. I do.
One question.
Uh-huh.
So you prove this non-negativity by proving that that is the CD index of some Gorenstein star. So
This,
How do you prove the non-negativity? Yes.
Oh, it's a trick. Let me,
Because, I mean, do you use the result by Carew?
no.
Okay, so it's an independent.
No, it's a different proof, yes. So essentially, so what goes into the proof is that this may be negative, but there's a lower bound in terms of Betty numbers.
I misread it. You wrote simplicial, of course.
Yes, I'm simplicial.
And if you're not simplicial, do you think that is still true?
I think it's true for homology manifolds,
Okay.
but you need algebra.
Yeah, you probably need some.
Yes. Yes, and if you want to talk about later, I can tell you what I think is the main difficulty behind trying to generalize that thing.
Okay, and one more question. So on the left, you wrote P is Gorenstein star simplicial. Think of this as phase poset of simplicial complexes. Maybe simplicial polytopes, you mean?
Simplicial polytope or simplicial complex.
But then.
Take a triangulation of a sphere, right?
Yeah, okay, perfect.
That's gonna work. And you can get away with a little bit less because you can, I mean, if you take, let's say a triangle with, the boundary of a triangle with two facets glued, that works. That's a simplicial poset. It's a bit more general. But for triangulations, it kind of, or it actually works. And so the proof of this is complicated. What happens is you have to use that, so the tricks. So I have 3 minutes. Okay, the trick, let me just tell you one trick and let me tell you one consequence that I think a lot of people will like. So there's the idea is we're gonna change these h's. Hi of p is greater than or equal than n, choose I. And for things to be Buchsbaum, I have to choose a field. And if I have a field, I can compute homology, but this is going to be greater than or equal than a sum from j equals to 2. No. Oh yeah, from j equals to 1 all the way to I. And this is not particularly important, but j minus I. I'm going to look at the Betty numbers in homology of this thing. Remember that this was the order complex, or the complex is actually the same over the field K. And so the trick is we're going to change. So we change these guys for this inequality over here, and it expands into a nice recursion involving some alternating sum of these guys over here. So it's an alternating sum of these phi n checks, and then what we have to do is a lot of manipulatorics to become, so there's several different interpretations of this thing. This has a nice recursion in terms of something called the Newtonian algebra, and it also has another combinatorial interpretation in terms of something called André permutations.
But that inequality is true for simplicial or for all?
No, this is true for simplicial. So this is actually, let me give this, so this is a result from Novik and Schwartz, and this is true for Buchsbaum simplicial. Posets. Okay.
Is Buchsbaum just Cohen-Macaulay with a new name on it, or is it something subtler than that?
And is the local cohomology scaled by the maximal area?
Yes.
Say that again.
Instead of being 0, the local cohomology is scaled by the maximal area.
Okay.
Yeah, it's a lot of manipulatorics, but let me tell you a nice corollary. Well, first of all, in the case of odd-dimensional manifolds, this non-negativity was an old conjecture of Isabella Novik. But this has a weird consequence because, so if P is an odd-dimensional, and here's the barycentric subdivision of a simplicial complex, of a simplicial let's say, manifold. So we said that these guys are actually Eulerian and have symmetric F vector. So I can actually ask what's the H vector of that thing. It's symmetric, and we can. So these barycentric subdivisions are flag simplicial complexes, and therefore have a gamma vector. So this has then P has non-negative gamma vector. So many of these things that we usually ask for homology spheres or for flag homology spheres, when you have a symmetric H vector, you could conjecture for manifolds as well. And let me say that, yeah, I'm 1 minute over time, so let me stop here, and if you have more questions, I'm pretty happy to address them.